Okay, so I am back, and we're still in this 3.3 section where we're talking about how to find the derivative of a function or the slope of the tangent line using a product rule, or today we're going to talk about the quotient rule. So, we talked about the power rule. The power rule says that if I have a term with an exponent, I can multiply the exponent by that coefficient, subtract 1 from the exponent, and I end up with the derivative of that function. The product rule says if I'm multiplying two separate functions together, I would have to take the derivative of the first function times the second function plus the derivative of the second function times the first function. You simply cannot just take the derivative of each function and multiply those derivatives together. That does not work. Similar story with the quotient rule. So it says if f and g are differentiable, meaning I'm able to find a derivative of those functions, then f divided by g is differentiable. I can find the derivative of this quotient as long as g of x does not equal 0, right? That's that domain piece of things where I would not be able to find a derivative where there's a vertical asymptote. So if in my original function f divided by g, the denominator, and there's an x value that makes the denominator 0, I would not be able to find the derivative there. That would create a vertical asymptote, okay? All right, so here's the rule. And again, it is not just a simple, I wish it were as simple. It is not just a simple take the derivative of the top, take the derivative of the bottom, and divide them, okay? So again, if I have y equals f of x divided by g of x. Okay, so I have this quotient. Again, g is not equal to 0. Then, okay, the derivative of this quotient, so y prime, is equal to, all right, it's kind of a similar setup to yesterday when we start. I have to take the derivative of that first function or that top function, okay, times the second function, or in this case, the function in the denominator. It's plain Jane denominator function, okay? But I'm going to be subtracting this time. So minus the derivative of that denominator, or that second function there, times the original top function, or the original first function, I suppose. The extra piece here is it's all divided by whatever that denominator is. In this case, it's my g function squared. Okay, so a little bit more to this particular derivative. And again, I like to get things in words, okay? So we say y prime is equal to that top function, whatever the derivative is of the top function, times just the bottom function, just a rewrite of that bottom function, minus the bottom function's derivative times, again, a rewrite of that top function, okay, all divided by whatever that bottom function is squared, okay? Excuse me. If you know these rules and you can stick to these rules, you will be great. You just have to know these rules, okay? So let's take a look at this first problem. It says f of x equals x divided by 1 plus x squared. And when we practiced the other day our whiteboard problems, I said, well, you could split this function up. But you can only split the function up into two fractions if there's a monomial in the denominator. And this denominator has a binomial. I cannot, and I do this, I repeat this because this has been an issue. This does not equal x over 1 plus x over x squared. These two things are not the same. It does not work in reverse, okay? If I had a single term in the denominator and multiple terms in the numerator, if this fraction were flipped, I could then split into two fractions. But the way this is written, I cannot split into two fractions, okay? So don't even try it. All right. Again, I need to end up having the derivative of the top. So I can go through the same process I went through yesterday. Yesterday I said my f function is x, and so f prime, that top function, maybe I do this because I already called the function f. So maybe I say top derivative is equal to 1. And then I would have to know what that bottom derivative is. And that bottom derivative would be equal to 2x. Okay, I'm going to use those pieces as I fill out this formula. So here we go. If I want to find the derivative of f, I'm going to say f prime of x equals, all right, I need the derivative of the top. The derivative of x is 1 times, I'm going to rewrite this bottom function, okay, minus, now I need the bottom derivatives. I need the derivative of that denominator, and the derivative of the denominator is 2x times the top function. So I'm just rewriting that x all divided by that entire original denominator, 1 plus x squared, squared. Okay, so I put that denominator in parentheses because I'm squaring that whole thing. Okay, my suggestion then is to clean this up, and I'm really just concerned about cleaning up the numerator. Okay, so I really can just go ahead and rewrite. This is 1 plus x squared in parentheses squared. I do not need to multiply that out. I'm just going to leave that as is. Okay, but I can clean this up a little bit. I get 1 plus x squared minus 2x squared. And I could really clean that up just a little bit more. Right, this gives me a negative x squared plus 1 divided by 1 plus x squared squared. No, even if I factor out a negative 1 from the top, it's not going to divide with a term in the bottom. So this is it. It's my final answer. This is what f prime of x equals. This is my derivative of the function f. I'm done. Okay. Well, let's do number 2. So number 2 is this e function. And remember, I said that the derivative of e is just itself. It's just e to the x, which I think makes this problem a little easier to muster. I have d dx, which is my directive. Those are my directions. Take the derivative of this function. And so I don't need any derivative notation. I can simply write equals. I'm going to go through this quotient rule because I'm dividing two functions. I'm dividing e to the x by e to the x plus x. Okay, so I need the derivative of my top function, which is e to the x. Okay, a rewrite, so times that denominator, e to the x plus x, minus the derivative of the denominator. So the derivative of e to the x is e to the x, and the derivative of x is 1. So plus 1 times my numerator function, all divided by that entire denominator squared. So that's my setup, okay? And if you can do the setup, then that is key, is getting that right setup. Again, I don't have any notation over here because I've just been given the directive to find the derivative. That derivative is equal to this right here. I'm going to clean it up. So when I do clean this up, okay, remember that when you multiply like bases, you add the exponents. E is a common base. X plus x is 2x, okay, plus x e to the x when I distribute. Same thing here. I get minus e to the 2x, right? I'm also distributing this negative simultaneously, okay? So I get a minus e to the x, all divided by, again, this e to the x plus x, that quantity is being squared. And I can clean this up just a little bit more, right? This e to the x, e to the 2x minus e to the 2x cancel. These things do not interact with each other. They're not common terms. They're not like terms. One has an x as a product, x times e to the x. The other one does not. So I simply write that this is equal to x e to the x minus e to the x, okay, over, again, this e to the x plus x squared. You can leave it here. I talked in my other video that sometimes you will see that x factored, or sorry, that e to the x factored out, so you could, but it's not necessary. I just like to be aware of those things, like in case it shows up in a multiple choice. In case it shows up in a multiple choice, I guess you could have, oh goodness, commonly you could have that e to the x factored out. So I guess you could have that this is equal to e to the x times x minus 1, and then again divided by e to the x plus x squared. You don't have to do that for me. I'm just making you aware that these are equivalent options, and sometimes you see that e to the x factored out. Just making, put it on your radar, okay? All right, let's do this last one. It says, use the table to the right to evaluate f divided by g prime of 7. And we saw something with a table yesterday with this product rule, okay? In fact, I think it's the same table. So again, my suggestion is that you could do this generically, right? So I could just go ahead and say that f divided by g prime of x would be this generic piece, right? That I would have to do the derivative of the top times the bottom minus the derivative of the bottom function times the top. Okay, all divided by that bottom function squared. And then I could go back in and say, okay, well now I need to evaluate this derivative specifically when my x value is 7. Okay, so I would be replacing each of these with 7. Again, you do not have to do that in between step. The step that I have in that black marker, you do not have to write that out. If you understand that anytime you write f or g, or f prime or g prime, and you're evaluating specifically at 7, that you fill the x in with 7. You can jump straight here. Okay? But I'm not done yet. I now need to go and say, okay, I need to fill this out. So f prime of 7 based on my table is 2. And g of 7 based on my table is negative 4 minus g prime of 7 based on my table is 5. And f of 7 is negative 9, all divided by g of 7. I'm going to put in parentheses, right? G of 7, that function is being squared. Now I can go through and simplify, right? I get negative 8 plus 45 divided by 16. And when I clean this up, I get 37 divided by 16. And again, just to review, that represents the derivative of the quotient f divided by g, the derivative of that function at 7. Okay, so be ready to use the product rule and quotient rule when I see you again on Monday. And again, we'll be in room 634.